Okay, so welcome back. Today, we finally get to these things called dense neural networks or deep neural networks. And this is kind of like everything we've done prior has led to this lecture where we start to stack together these single neurons to create one of the most general and powerful function approximation tools. And again, that's what machine learning is all about, finding function approximators, right? So let's go ahead and get started. All right, so what are these things? Well, obviously we know what a single neuron is, right? We take in feature vectors and then we spit out a possible label, and we can train the weights and bias with some form of gradient descent, okay? Stochastic gradient descent. Well, these deep neural networks, or in our case, dense and deep neural networks, are simply layered single neurons. So imagine like in this diagram here, so the far left is your input layer. That's just like any single neuron, right? We have an input layer, right? And if you look at the top light green node, you'll see that if you get rid of everything else, that's a single neuron, right? And then right below it, there's another single neuron. Right below it, there's another single neuron. And there's weights and biases connecting all of the inputs to that first layer. And it works the same. It just now so happens to be the case that you get a vector out, right? You calculate all those single neuron outputs and you get a vector. And that's kind of stored in that next layer. And that layer acts as an input layer to the next layer, which acts as an input layer to the next layer. And we end up with an output layer at the very end. So these are actually these are specific instances of something called a computational graph. These computational graphs have been studied for a very long time, and you should just know that that's what they are, okay? So they're also, as I just mentioned, you have an input layer, a sequence of hidden layers consisting of multiple single neurons, and then an output layer, okay? That's what I was just saying. And through performing this process of, you have input layer, linear combination, apply some activation function, that's your next input, apply linear combination, and then you get, and then apply another activation function. By sequencing this together, you get a composite function. And I'll elaborate more on that in a moment. Okay, so, but before we do that, what are they used for? Well, in supervised learning, these things can work both with regression and classification tasks, right? And we should assume as such because single neurons can work in classification and regression tasks. But these have a little bit more power to them. You can even perform dimensionality reduction, such as the singular value decomposition using these network structures, right? So imagine you have a matrix and you want to decompose it into smaller pieces. Well, what you could do is you could feed into a network a matrix by flattening it out or some other form of that, and then make the layers get smaller and smaller to the meet in the middle and how many dimensions you want it to be at, and then mirror that out and then compare your input to as your output. In the middle, you have a reduction of that matrix. These things are also used in deep reinforcement learning, which is kind of my favorite topic in machine learning. And I encourage you to go and watch the documentary about AlphaGo by DeepMind. That documentary really inspires me to think about machine learning and keep a passion for it. And the soundtrack's awesome too. Like a lot of times when I'm programming, I have it playing in the background because it's nice to have like a little motivation back there, right? Okay. So how do they work? Oh, before I do that, let me show you this link here. So TensorFlow Playground is this thing, and this is a neural network, right? So these are the layers. It's kind of arbitrary. You can add layers. I mean, add nodes and layers. You can even add more hidden layers. But we have input and we have output. And suppose like we're trying to classify whether or not you are an orange dot or a blue dot, right? Now, with all of the single neurons that we've looked at, these would be considered linear models, right? They're finding a linear, like a hyperplane or a line that separates the data. That is clearly not linear, right? But because of the composite nature of this function with non-linear activation functions, we should get close to something. So I clicked on that little play button and it's training right now. So you can see the regions of space that it's predicting to be blue and orange changing over time as each epoch finishes, as stochastic gradient descent is being. And it looks like it's starting to get there, right? It's not having an easy time, but it's definitely getting there, which should be like very surprising considering all the things that we've been finding are just hyperplanes or lines. So maybe I'll let it run a little bit longer. It's starting to get there, but we can like change it up to make it run faster. Like suppose we want to do like this. Like that's clearly not linearly separable. I just clicked on this little icon here, and then it finds it like immediately, which is pretty cool, right? So neural networks in classification can find pretty much any separating function that you can think of, which is awesome. Like no matter how complex it is, they will find it. But we will run into the problem of overfitting because of this. And that's where test, train, validation data is really important. And we haven't really done that yet. We've just been trying to get the things to work. But starting from here on out, we have to be very conscious about testing the algorithm after it's learned, because especially with deep neural nets, you will overfit the data. It'll just completely learn the thing, and then it's just to be cautious about it. So back to here, I have another link that I wanted to show you, like kind of what it's doing. So imagine you're looking at, maybe I should make this a little bit bigger. So imagine you have digits, like pictures of digits, and you're trying to like classify them. And in the very last layer, you have an output of 10 entries in it, right? So you output a vector, of the 10-dimensional vector. So as the neural network is training, it's placing these out vectors somewhere in space. And you can see that like digits 0 are already like being placed over here. And over here, there's like, it's being jumbled. So what are those? Like maybe looks like 3s and 8s are kind of near each other, which would make sense, right? The 1s are starting to branch off together with, what are the other ones going there? 7s. So that makes sense, right? 7s and 1s are going to the same region of space. So this is what's happening over time, right? It's trying to place, like project them into space and separate them. Now, this is a different viewpoint that we haven't thought of yet because we've just been outputting like one thing, right? And we've been looking at the separating hyperplane. What these things are doing are allowing us different interpretations of the classification problem. Not only are we finding separating regions, but we're also mapping the feature vectors into like positions in space, which then we could classify on. So maybe there's like another, I think there's like, yeah, so this is a pretty cool illustration here. So this is like this MNES data set that we're going to talk about today. So like 7, right? So if we just like, I don't know, what's being fed in here. So 1 is being fed in here. There's other things we're not going to do over here, but the output is still the same that we're going to be looking at. So notice how this entry here is getting higher and higher and higher over time as it's training. It starts off low and then it starts to get higher. So it's placing emphasis on that entry of this 10-dimensional vector, which means that entry is going to push it into that dimension more than the other ones, right? So it's as it's making the entries in the vector higher in some places and lower in others, it's pushing the vector in space, okay? So maybe there's one more I wanted to look at, I think. Again, it's just shooting them all over the place, just trying through observing what it should be, adjusting to place it in the right dimension, where they're kind of clustered together. And which, again, going back to what I said earlier about dimensionality reduction should make sense now. Like you can take a big thing and map it to something small, right? So that's how they work. So each input signal or a feature measure is scaled by the first layer, which in turn is passed into an activation function, which forwarded to the next layer, so forth and so on. This process continues until you get an output. And I'm mentioning again, passing a signal through the layers of a network creates a highly composite function trying to approximate some target function. Now, just like as with the single neural model, so we're going to optimize the weights and biases on each of these layers through stochastic gradient descent. It just turns out that finding that gradient is not the easiest thing. And that's what we're going to start with today, and you're not going to like it. But I tried my best. I spent like hours, and I don't know how many hours I spent on this PowerPoint to make sure that it's clear to you. But before doing that, I should mention this universal approximation theorem. This is a theorem that to kind of, I'm not going to state it exactly. I'm just going to give you an idea of like what it means. So imagine these G's are the functions computed in layer M, right? So layer M has a bunch of nodes on it, and so there's going to be M activation functions, right? And a particular node H in the next layer that's the activation function in the next layer at one of the nodes. So then if you think about what H is activating on, H is taking as input a vector, and each entry in that vector was the output of another function. So it's a composite function, right? And here, the use of nonlinear activation functions is key. If all functions are linear, then we can actually show, and it's not hard either, to show that a network is just linear regression, just standard linear regression, right? If all of the activation functions are linear. And this is the part that I need to emphasize here. It has been shown that a network with at least one hidden layer of nonlinear units, and you can choose from any number of things that squish the signal, like the sigmoid function, or something called the ReLU function, or anything that you can think of that squishes the thing. As long as you have one layer that has these nonlinear activation functions, then these neural networks can approximate almost any reasonable function. And that's sort of the statement of this universal approximation theorem, which to us as people like practicing machine learning, that's good, right? Our whole goal is to find this target function that we don't know. And this gives us a tool. So now to introduce you to the details behind the process of feeding in data and then also calculating the errors at each layer, we're going to start with a very simple example. All right, so we have, as typical in supervised learning, we have a set of feature vectors and labels. And we're going to assume for this simple example that our input vector has 3 measurements, okay? And for the labels, we're going to one-hot encode the labels. So for example, if we were looking at digits and the labels were either 0 or 1, right? Those are the labels given to like a picture of a digit. Then we could one-hot encode the label 0 with the column vector 1, 0, where the one entry emphasizes that that's the label, right? It doesn't have to, it can be like a shoe versus a shirt. It's just a way of giving it a vector label so that we can think about how those vectors are being projected in space and separating them through training. Does that make sense? If it's not clear, it will become clear when we actually program this stuff later. All right, so here's our simple network. We have one input layer, and we have an output layer and a hidden layer. However, in this case, think of this as 2 hidden layers, and the output layer is really the y hats there. So that's how I'm going to do this. Now, the notation and terminology for neural networks is all over the place. So I have to preface before going forward that this is my notation. This is the best way that I found to learn this stuff when I was teaching myself. I took ideas from certain textbooks, certain things written online, and distilled it down to something that could be teachable and understandable, because everything out there is a mess. The notation's a mess, the terminology's a mess. So just, that's a warning, but I think that you'll be able to understand it with the notation that I have. So I'm going to say 2 hidden layers, an output layer, which is the Y's, and 1 input layer, which is the X's. Okay, so weights and biases will be initialized randomly from a normal distribution. That's important. And we're going to say L is equal to 3 here. Okay. Right. There's 3 layers. So capital L is going to denote the number of layers, and it's inclusive to the input layer. That's my terminology. Okay. All right. So the feed forward phase. This is the first thing we have to learn before we can start talking about any type of gradients. So suppose we have a feature vector xi. I'm going to denote that by a0. Okay. And notice how a0 goes in, and then we have z1, a1, and then z2, a2. Okay. Now, how do we denote the weights? Weight at layer L subscript ij. That reads to me the weight at node L from, so sorry, the weight at layer L to node I from node J. To node I from node J. So the first index is where you're going, and the second index is where you came from. Okay. And you can see that just observing the weights in this diagram, that's the notation that kind of, it makes sense. But the reason why I chose that notation was, well, we'll see in a moment. Bias I is just the bias connected to node I in layer L. Okay. So hopefully that's clear as well. And notice that there's bias on each hidden layer. Okay, so the pre-activation is simply the weights connected to that node times the inputs along those weights plus the bias connected to that node. The indices make it look awful, right? It's not, but if you think about it, just like focusing in on, like, maybe I'll have to exit out of the screen here, but like focus in on like Z1. So it's like A1 times this W plus A2 times that W plus A3 times that W plus that bias goes into Z1. Okay. Now it becomes a lot cleaner to write it as a matrix vector multiplication. And this is why I chose that notation for the weights, because look at the entries of the matrix. The subscripts are the entry numbers. Weight 1, 1, weight 1, 2, weight 1, 3 along that row. The subscripts match up to the entries. And if you look at that product, it is the linear combination of the columns, right? A0 times the first column plus A2 times the second column plus A3 times the third column plus the bias vector. And then we just apply our activation function to that vector Z to get our post-activation value. Right, so there's an activation function, just like with the single neuron model. Okay. And then in a similar fashion, now those A's act like the previous A, right? It's the same exact thing. So we can write another matrix multiplication here. So actually, before I should probably go back, notice on the far left-hand side, Z1 equals to W1 times A0 plus B1, okay? Z2 is W2 times A1 plus B2. Do you see how the the superscripts are matching up? And then the same thing with the post-activation, it's just applying some nonlinear function to the pre-activation. Okay, so given a point, initialize A0, or the first A. And then for L equals 1 to, little L, 1 to big L, compute the pre-activation. with that clean formula. It's a linear combination, right? And notice how it's similar to the single neuron, right? Z is equal to W times your input plus bias. That's what it is. And then you pass that into an activation function to get your post-activation value. And then you predict out the last A that you found. Okay. Just as before, with the single neuron, you apply the activation, you get your post-activation, and that is your output with the single neuron. All right, so we need a cost function now, right? And there are all sorts of cost functions. We could use cross entropy loss, not the binary version. Well, actually, in this case, we could use the binary version, but in general, we can use other versions. But for simplicity and just educational purposes, I'm going to use the squared error cost function. So notice it's a sum now, right? And that's because we're outputting two things, y1 and y2. So we're going to compare the y1 hat minus y1 true label, square it, and then y2 hat minus y2 square it. So we're comparing the entries now of the vector, not the single number. Does that make sense? Yeah.
So are we making the assumption that the activation functions like between the layers, are they necessarily the same?
They don't have to be the same. But good point, because I almost missed it. I'm saying that our activation function is the sigmoid function across the whole layer, across everything. So that's the only activation function we're going to choose. Again, for some simplicity, because we know it well, the derivative is easy to write, and it'll work for the task that we have later. Okay, so here's where it starts. We need to find the gradient of, again, this entire network is a function. It's a function of every single weight, right? How many of them are there? There's 2, 4, 6, 8, 10, 12. There's 12 weights and 4 biases, right? So our cost function really is a function of all those weights and biases. And we need to somehow calculate the gradient of that thing with respect to each of them, right? So it's going to be a big, tall vector of entries, right? Or if you think of it as a, yeah, well, I'll leave it at that. I'm not going to talk about Jacobians or anything like that. So, all right, here we go. We're gonna figure out how to do this by focusing in on one of the weights at a time. If we can find the gradient with respect to that weight, we can probably find the gradient with respect to every single weight in that layer. So I'm going to take the partial derivative of the cost function with respect to weight 1, 1 in layer 2, okay? Which is equivalent to applying this operator to that sum. So far, so good. In that sum, we only have 2 outputs, so that's what the sum is. So it's easy to see, right? And then it's a linear operator, so we can distribute it in there on each of those terms. But we really only have to focus in on what term? The first one, right? W11 in layer 2 only contributes to Z1, and Z1 contributes to A1, right? It does not contribute to the second term, so it goes to 0 when you take the derivative, right? Again, the first, so maybe it helps with my mouse to, like this piece right here is a function of W11. This one right here is not, right? W11 is not connected to that node, so that piece has derivative 0. So then what's going on here? Well, derivative of the outside is 2 times a half, right? Chain rule, very important, times the derivative of the inside. The inside, the only thing that is a function of W11 is A1 right there. But A1 is the sigmoid function applied to Z, right? So the derivative of A1 is sigmoid prime of Z. Does that make sense? Because sigmoid of Z is A, so we're taking the derivative of it. And then, so it's the derivative of the sigmoid times the derivative of the inside, right? The chain rule one more time. So it's three applications of it. 1, 2, 3. And we end up with the partial derivative of 1, 1 with respect to W11 of Z1. And it's just that. It's the coefficient of W11, which is the A, right? A times W plus B. A times W plus B. So the coefficient of that W11 is that A1. Make sense? Okay. And I'm going to introduce something now to help us. I'm calling it the output error. Okay. This is if we have capital L layers, I'm saying delta of L subscript 1 is equal to that term right there. The difference between the output times the derivative of the activation function that gave us that output. Now, this is actually something we've seen before, right? We've seen, think about it, like y hat minus y times the derivative of the inside, which happened to be in all of our cases just x, right? It's the same exact thing. So this is like that value there. And A1 right there is like the x, right? In all of our previous single neuron examples, it was the y hat minus y times the derivative of the inside, and then there was an x there, right? It just happens to be now that x is A1, right? Does that help at all? So this error is going to be useful when we try to figure out how to find the derivatives in the next layer behind us. Okay, so, all right. I think it might actually help for me to not be in full screen mode so I can like mouse over the things as I'm talking. So, okay, next let's try to find this derivative here with respect to W12. Again, so I'm going to apply that derivative to both sides of the cost function. All right, looking at this term, notice that this edge is connected to this node, right? So that means that this is the only piece that's going to be meaningful. This piece is going to be 0 because A2 is not a function of W12. Okay. As before, derivative of the outside times the derivative of the inside, right? A12 is equal to sigma of Z1. So the derivative of the inside is sigma prime of Z1 times the derivative of the inside. And as before, it's just A, right? A2 in this case, because A2 is traveling along that edge. But notice what's multiplying A2. It's that same output error, right? So the partial with respect to W12 is that output error times A2. The bias, can you just take a guess at what you think the bias partial derivative will be? In the past, what's been the difference between the partial derivatives? Partial derivative with respect to W, there was an X multiplying it, right? It's a 1, so it's just going to be the output error. That's it. Okay. So that's just like we've done before, right? So that computes all of the partial derivatives that are connecting to that top node. Okay. Now let's consider the ones connecting to the bottom node. So taking the partial with respect to W21. Now, which piece matters? The piece with A2 now, right? Because A1 is not a function of W21. So the first piece here is going to go to 0, and we're going to look at the second piece. And as before, derivative of the outside times the derivative of the inside. And then again, times the derivative of the inside. So now the coefficient in this case would be A1, right? Because A1 is traveling along that edge. And when I say traveling, I mean A1 times that value on the edge plus the box, right? But so now looking at this, we have another output error, a different output error. Notice the 2s, right? The other output error was the 1. So we can extrapolate this, all the other derivatives now, right? The output error, so the derivatives of all of these edges here connecting to node 1 and layer 2 is just the output error at node 1 times the respective entry that's going into it. So in general, these are our last layer partials, right? We just have to remember what that error is. And it's actually really easy to remember. It's the derivative of the difference, right? The y hat in a sense, but I'm calling it a, so it's, I didn't want to like have so many lines. Just a is the same, al is the same thing as y hat l, right? So y hat minus y, so the derivative of the outside, so the 2 times the half, times the derivative of the inside, and then wait for the coefficients. That's the output error. That's what I'm going to call it. And we can compute this with what's called a Kronecker product, which is just entry-wise multiplication, right? So here, this notation here, nabla subscript a, is the gradient with respect to that a, or c, right? We can take the gradient of the cost function with respect to a, which is 1/2 that difference all squared. The gradient is just the 2 multiplies the half, it goes away, times sigmoid prime of z of l. Okay, that's, so this is a vector representation of the output errors. Okay. All right. We're almost there. This is the one that's annoying. So we can compute the gradient of this function at the second layer. Now we have to do it at the first layer because those are also parameters of the model. So let's take the partial derivative of the cost with respect to W11. But notice now that W1 travels along these lines here, right? It goes to both these outputs, both of them, okay? So we have to consider both of them, which hopefully by now, that looks okay to you, right? It's the derivative of the inside, derivative of the outside times the derivative of the inside times the derivative of the inside again. And this is why the deltas are nice to have, because those values here, those are just the output errors, right? The deltas, right? The difference times the derivative, difference times the derivative, respectively. So I can rewrite it like that and just, I wrote it completely out right here so you could see it easily, that Z1 is just A1 times W11 plus B1. So when you want to take the derivative with respect to 1, it's just that coefficient there and that coefficient there. Okay. So what did I do here? Oh, yeah. Sorry, I was a little bit off. So this Z2, that's this Z right here, right? That's why I wrote it out. We're taking the partial of this Z2 because that was where we're at in that layer, layer 2. And Z2 is precisely this, right? So when we apply this derivative here, it looks misleading, but pay attention to the superscripts, right? This is W11 in layer 1, right? And A1 is the only thing, is a function of that. So when we take the derivative here, the B goes away, but the derivative of A1 is W11 in the second layer. And then we take the derivative of the inside. The derivative of the inside is sigmoid of Z1. And the same thing on this piece over here. Okay, I know it's a lot to take in, but it's really just composite on each other a bunch of times. But we're in luck because notice that this derivative here and this derivative here are the same. So we can rewrite this sum as a vector product times this, right? Derivative of sigmoid is sigmoid prime times the derivative of the inside. And the rest of it is precisely the sum. That times that, plus that times that. And then you distribute that across. And that gets really small. Maybe I can make it like a little bit bigger. No, I think you can see that. So Z1 is really this value here. Looking at all those values, the only one that's the coefficient of W11 is A10. So we arrive at something called a neuron error. So output error was the very last one, and then we have neuron error. Okay. And the neuron error is written in terms of the previous or the next layer's errors, right? We see that right here. So these are the next layer's errors, right, in that column right there. So we need those to compute the errors here. But it's really the same idea. The output error in this, it's the same idea. It's just passing it back. This is why it's called backpropagation. We're using the output error to calculate the error at the previous layer, which we can use to calculate the error at the previous layer, use it to calculate the error at the previous layer. Okay. And then that gives us our partials everywhere. If we know the neuron error, then we know the partials. And look at how nice that looks. Right? The partial with W, there's the coefficient A. That's like the X in our previous single neuron models. In the bias, there is no coefficient. It's just the error. Right? It's y hat minus y. It's the same idea. Okay, so back to full screen. So how are we going to calculate the gradient now? So given a feature vector, we initialize a knot. We feed forward and compute the pre-activation vectors and post-activation vectors at each layer. We compute the output layer. The output error once we do that, and that's easy to do. And then we use that error to compute all the previous errors. So we get a bunch of error vectors. And once we have those, we update the gradient, right? Again, it's in vector notation now, but it's the same idea. Error times coefficient for W and just the error being subtracted off, well, times the learning rate for the bias. Okay, so I know that it's a lot, so I'm going to pause the recording. Okay, so before moving to the coding, I just want to make note on the recording that earlier this was W1, 2, it should have been 2, 1, and I changed it. And now the indices match up as they should. And the same thing for the second layer, 2, 1 instead of 1, 2. Okay, and thank you for pointing that out. Did not catch that.